Welcome to the Canadian Tech Journey, your ultimate destination for unlocking the mysteries of technology. I'm Gurpreet and I'm thrilled to embark on this journey with you.
Okay, in this episode, I want to talk about RF characteristics. See, I always want you to understand that anytime you're trying to learn any new technology or anything which is new, what I've seen with my own experience is if you start to go ahead and answer that question of why, it always makes your life that much easier. So, why do I care about RF characteristics? Because, see, think about this, Wi Fi is a wireless technology which works on RF. RF is electromagnetic waves. When I'm transferring data from one end to another, I don't need a physical cable, right? This is why we need to understand RF characteristics, because when we're using those electromagnetic waves, there are certain properties or there certain characteristics that electromagnetic waves have that I can change, so that way I can try to transmit that same message on the other side from one side. And I'll give you a couple examples as we go through this episode. So let's dive into it and understand that what kind of options do we have here. So first of all, as I mentioned, if you're talking radio frequency, which really means it's an electromagnetic wave, I won't go over what's written in the slides. You can read that up and pause the video and read that up if you like. But the idea is it is wireless and we're trying to use RF frequency to be wireless. Now the characteristics that we're going to talk about are wavelength, frequency, amplitude, and phase. We'll go one by one and then we should be clear on what these are. See, wavelength is pretty much distance between two successive points, right? Now, what are these points? So the point is when you have a wave, which is like a sine wave, and I'll show you a picture in a minute, it's represented by lambda. Also, something important to understand is the higher the frequency, the smaller the wavelength, which means they are inversely proportional. So in Wi-Fi, so far, we have been using mainly 2.4 and 5 gigahertz. So if you look at 2.4 gigahertz, which is a lower frequency, it has a higher wavelength, almost 5 inches. When you talk about 5 gigahertz, about 2 inches. Now, if you look at the 6 gigahertz, which is also coming out pretty soon, and I can see the adaptation for that one as well, you'll see little less than 2 inches, right? So that proves the point that, it is basically inversely proportional. So if one goes higher, the other one goes less. Okay. So distance between the 2 points is, as you can see right here. Okay. If you look at the diagram at the bottom, now you will notice that the distance between the two peaks is going from higher to smaller, right? So that's the main difference. Some more pictures for wavelength, and if you notice that if you have a FM or a radio tower AM, you see it uses a much lower wavelength. That's why the distance is also much higher from a perspective. The frequency is much lower, and that's why the wavelength is much higher, right, as compared to a Wi-Fi. Because it's in gigahertz and versus that one is in kilohertz. So that's something to remember, and that's why this relation between frequency and wavelength is important. So what is frequency? We kept talking about frequency while we were discussing wavelength. So see, frequency is if you have a second, how many of these waves can I pass through them? If you look at this one here, I see about, say, 1, 2, 3, 4, 5 there. And as soon as I see at the bottom option, I see only maybe one going through the same time, right? So the frequency is higher here, and the top one, and the bottom one, the frequency is lower. Now, we already spoke about that relationship. The only thing I didn't speak so far is what's the formula? What exactly is the formal formula for this? So it's lambda, which is wavelength, is equal to c by f. C, which is a constant value for speed of light, and then you have frequency at the bottom. But again, the point to make is, see, the constant is not going to change, but since lambda and frequency is inversely proportional, that's what we need to remember. So again, if you don't like maths, you don't want to remember any of this, don't bother. Only thing I want you to remember is if the frequency goes higher, the wavelength drops. The wavelength goes higher, the frequency drops. As long as you can remember that, you're good. The next thing is amplitude, the strength and power of a wave, right? Typically, what you need to remember is from our perspective, since we're working on Wi-Fi, so I want to talk Wi-Fi for a second, is the transmit power that you see is much lower, right? It's not much. And also, as we go further in these episodes, you'll notice that once the signal comes out of an AP or any transmitter, it has a significant drop. So by the time you get it, it's in negative, because we look in dB. We haven't spoken about that yet, but we will. So that's kind of the strength of the signal. So it's pretty lower. If you look at it, the first picture at the top, the amplitude is higher, and the bottom option, the amplitude is much lower. So that's what you need to remember. Okay. We spoke about the three things. fourth one would be the phase. Phase is a little different because phase involves relationship, right? So if I say, okay, I am gonna be weighing 70 kilos, that's just my weight. But that's just a value, right? Unlike amplitude or a frequency or a wavelength. But if I say I'm 5 kilo lighter than so and so person, now I'm talking relationship, right? I'm 5 kilo heavier or lighter as compared to that person. So these are the kind of things that you need to understand from a phase perspective, and I'll show you a little diagram here, which really puts the point home. So for example, in this case, I have this wave, right? If I increase the amplitude, I see the power goes up and low, right? That's our amplitude. So I'm changing the amplitude. Now, if I change the wavelength, you notice that the frequency will increase, right? If I'm decreasing the wavelength, the frequency is increasing because I see more peaks between this. If I take it all the way at the end, I see only 4 signals passing by, right? So amplitude, wavelength, frequency, talked about those. Let's move to our fourth option, which is this guy right here. So I'm saying I have 2 waves, right? So I have 2 waves. Let's say if they were in phase, I don't see the red one. What happened? That's just because they are in phase right now. So they're just top of each other, right? That's how it's going. But as they start to go in a phase difference, like for example, if it goes to 90 in this case, you can see that there's a little bit of gap. One is lagging behind the other, right? And if I take it all the way to 180, one starts to go up, the other one starts to go down, right? So that's again phase, because it's relative to something. So green relation to red in this case, right? When talking wavelength in this case. So let's get back to slides again to wrap this up quick. Giving the same example, right? So the main signal that's in phase, exactly, that's 90 degree outside, 180. That's exactly what I showed you in that demonstration from that website, which is pretty cool. And then you have this carrier signal, right? Data consists of zeros and ones. How can I change these properties and start to transfer ones and zeros? Because as long as I'm able to transfer 1 and 0, I'm able to kind of go ahead and send data wirelessly, changing the RF characteristics. As we mentioned, radio frequency is electromagnetic radiations, with different properties that we looked at. These properties can be changed over time. This is modulation. Okay, this process is called modulation. I can change those properties. Now let me tell you a little story here, or a little idea that you can imagine. Think for a minute. If you had 2 friends, they're 10-year-old boys or girls, whatever you want to call them, they live right across each other, so their bedroom windows align. Because they're 10, they have to go to bed at a certain time, so the parents won't be happy, but they want to talk. The way they do that is, let's say they have flashlights. First one, points the flashlight on the other one's window and flashes it twice. Say maybe that's high. And if he does, and that he replies back with 2 flash, that's high back. Similarly, you can start coding, right? Now, turn off and on 3 times, 4 times, 5 times. You can think about this as a little code, that each flash means a little code. Now, how many times can I really change these things? It becomes hard. I want to send bigger messages. So now what about if I start, so let's say the flashlight was yellow in color. I can start putting paper in front of it, like a blue color versus a green color versus a red. Now that could mean something different. So if I flash it twice with a red, that might mean something different as compared to the other one, right? Another way of doing that is if I start to say point out towards your chest and your head, that could mean again something different. So I'm trying to combine these different combinations, and I can start to code much more bigger conversations now, right? So this is exactly what we do with modulation when we start to add a few things, like when we go into higher speeds, like we're changing the phase and the amplitude at the same time. Now I can encode much more data, much more bits, which means I can go much faster now. So the data rates are much faster now, right? This is pretty much what is modulation, right? So I hope that example helped clear that thing up a little bit. Keying methods, again, as I said, these are the kind of things that I can change to, the properties I can change to modulate, right? These are them. So I can change amplitude, I can change phase, and I can change frequency in this case. And then there are current state and state transition. So current state means what is my current state? So if I'm using amplitude, if the amplitude is high, means that's my 1 maybe, for example. Or as soon as the amplitude changes from high to low, that means I need to change my bit from 1 to 0 or 0 to 1. Similarly with the frequency, right? Or similarly with the phase. So give you example here. I'll skip through that slide there. So right there, right? So if you see the frequency is going higher, it might be ones. And if they go smaller, then that might be zeros. If you look at this one here, same thing. Frequency higher, lower might mean 1 and 0. Phase shift would be an interesting one here, is because if you look at this, if you follow the wave, as soon as the wave changes, the value changes, right? So the current state is whatever 0. As soon as the shift changes, it's turned to 1, and I'm going the same way. It was supposed to come down here, but it again went up, so it changed from 0 to 1. So that's just a way of me changing these wave characteristics, and that way I'm able to kind of translate ones and zeros on the other side, right? Now, as I said to you before, is obviously every time I'm changing, I'm just changing one thing. But if I start to combine a little bit more, like if I change it by 90 phase versus a 270 versus a 180, now I can change it from 01 to 00 to 10 to 11. So again, each change could mean 2 bits now, which means I'm double the speed now. So changing these will help me change the speeds better. And in the next episode, we'll look into some other things. That's all I had for this one. Thank you. And that concludes another insightful journey through the world of technology with Canadian Tech Journey. I hope you've gained valuable insights and a deeper understanding. Remember, the learning doesn't stop here. Keep exploring, keep cautioning, and keep learning. Feel free to subscribe to the channel for more exciting content and updates. Thanks for joining me on the Canadian Tech Journey. Until next time, keep learning and stay curious. See you in the next adventure.